So my paper is Mutation Selection Strategies and Mutation Testing. It's actually the fourth in the series of related papers on the effectiveness of random selection in mutation testing. The third was presented here last year, so it's good to be back. By way of introduction, I want to talk a little bit about mutation testing. I got some feedback last time that a lot of people don't really know what it is in detail. So I want to talk about that, the redundancy problem, the equivalent mutant problem, mutation adequacy, which is really where my novel contribution is, and the experiments and the results. So mutation testing in the large is used to assess the quality of unit test sets. Mutants are variants created by introducing faults into copies of the original program, and their mutants are killed by unit tests when they detect the faulty behavior. The more mutants a test set kills, the higher the quality. And we measure that traditionally with the mutation score, which is the number of mutants divided by the number of mutants that exist, or the number of killable mutants if the distinction is known. And then when you can iterate on this process, when you have unkilled mutants, you can write new tests to kill those and improve the quality of the test set. Here's a real simple example. Again, I apologize about the pointer, but the top there, this very simple Boolean expression, number is less than 0. We can mutate that any number of ways, as you see going down the side. I've just put 10 or 11 there. But we can also test the efficacy of our unit tests by executing them against these mutants. So on the right side now, you'll see I've made a little method is negative and embedded that Boolean expression in there. Basically, it's the definition of negative. And at the bottom right, you can see the 2 unit tests or assertions where we execute is negative and determine what value we want to see come back. And if we run those tests, then we'll see these results. You see now in the red, killed means a test failed, which is good in this case. You want it to fail because you want it to detect the faulty code. And in this case, the 2 tests have killed 8 out of the 10 mutants. So the mutation score is 80. And the logical question then is, well, can we kill the remaining live mutants? And so we examine them, we see what kind of test it elicits, and we add a third test, which does kill the 2 unkilled mutants, or the 2 live remaining mutants, and gives us a mutation score of 100 and renders our test set mutation adequate. So mutation adequacy is if your test set can kill all the killable mutants. So the redundancy problem, historically, this has been a big problem in mutation testing because, as you see, it creates a lot of mutants. Again, at the top, you can see our basic Boolean expression that we've generated 10 mutants from and could generate even more if we wanted to. But as you see on the left there, the second bullet, research shows that the complexity of mutation testing is order of n squared, where n is the program size. So obviously, the bigger, like imagine if our simple Boolean expression were a compound Boolean expression, or multiple lines if then else kind of structure, how many mutants could be generated? So historically, it was a problem in terms of resource capacity, less so today, but it's still a problem in a number of ways. Well, let me back up a second. You might say, well, what exactly does redundancy mean? If you look at mutant number 1 there at the top, and at the far right, you'll see test number 3 is the test that kills it. Remember, that unkilled mutant elicited test 3. And then if you look at the next line down and note that mutant 2 then is also killed by test number 3, we could say that mutant number 2 is redundant, because if mutant 1 is sufficient to elicit test number 3, then we don't need mutant 2. And if you drop farther down, you'll see, there's 4 or 5 other mutants that are killed by the same test. And we could argue that none of those are necessary as long as we have mutant 1, because mutant 1 will require test number 3 to kill it. Well, it turns out we can formalize those relationships with something that's known as subsumption. The definition on the left there, if a killable mutant is killed by every test that kills another killable mutant, then it is subsumed by the other mutants. That may sound a little wordy to say they're killable and they're killed by a test, but killable only means if they're not killable and there's not a test to do that, they don't end up in our test results to evaluate in terms of these subsumption hierarchies. But going back to the first example of subsumption, you notice mutant 1 is killed by test 3, as is mutant 2. We talked about that a minute ago. But mutant number 2, then, in terms of our subsumption definition, is killed by every test that also kills mutant number 1. So we can say that mutant number 1 subsumes mutant number 2. And as long as mutant number 1 exists, we will have to execute test number 3 to kill it, and it would in turn kill all those other mutants that kill test 3. If you drop down a couple lines, you see that mutant number 4 is also killed by test number 3. And again, it's test 3 is the only one that kills mutant number 1. So we can say that mutant number 1 kills, mutant number 1 subsumes mutant number 4 as well. I'm going to advance to the next slide because I think without a pointer, this will help it make sense a little better, because we can graph these relationships I'm talking about. So again, if you look at the upper and leftmost node in the graph, you'll see mutant 1. And the outbound arc indicates the subsumption relationship, and in the next node is mutant number 4, right? So we know, we can infer from the graph that mutant number 1 subsumes mutant number 4. And we know that from analyzing the test results of the first handful of mutants. But take another look in terms of the subsumption definition. Remember all the killable mutants. Every test that kills mutant 4, test 2 and test 3, those tests also kill mutant number 2. So mutant number 4 also subsumes mutant number 2. So mutant 1 and 4 subsume mutant number 2, and you can see mutant number 2 down at the very bottom the leaf node in the graph. You'll see mutant number 2, and again the outbound arcs of each node tell you which subsumes which. So because of the missing pointer, I fast forwarded here, but the graph on the left is all of the subsumption relationships that exist in the test results on the right. If you notice, the leaf node again has 2 mutants in it, and that's because they're essentially identical or indistinguishable based on the test results. If you look at the test results, again, I apologize about the pointer, mutant 10 and mutant 2, they're both killed by exactly the same set of tests, and in this case, all 3. So they are indistinguishable in terms of the mutation testing, the unit tests, and that is another form of redundancy. So we only need one of those 2. And in fact, based on the subsumption definition again, every test that kills mutant 2 kills mutant number 10, but in the inverse is true in this case. Every test that kills mutant 10 also kills mutant 2. So 2 and 10 subsume each other again, and they're identical, so they can coexist in a node together. And the same in the top nodes, 1 and 8 and 7 and 10, those pairings, they are also indistinguished from one another. So this helps keep the graphs simpler, because with thousands of mutants, you can imagine, this is a very simple example. With thousands and thousands of mutants, these graphs can become they're just inaccessible visually. Okay, so this slide, subsumption graphs and dominators. Dominator mutants are the top nodes in the graph. You notice they subsume others, but they are not subsumed themselves. The mutants grouped in the nodes subsume each other, as we just described, but the node they reside in is not subsumed by anything. And the takeaway here is that if you with your unit test, target one mutant in each node, you succeed in killing all the mutants in the entire graph. So it's the most effective, most efficient way to conduct the unit testing. The problem is that at this point, it's a theoretical exercise, because to determine the dominators, you have to analyze all the mutants, kill them all, analyze the subsumption relationships in the testing results, and then you can determine so in other words, you do all the work that you had planned to save to determine what they are. So again, theoretical exercise, but it's there is research going on to try to identify dominators automatically with machine learning and so on. So it's hopefully not theoretical forever, but it is for now. Anyway, so the equivalent mutant problem is a bigger problem, and it's long known, it's researched pretty thoroughly, but looking at the bullet comments on the left, equivalent mutants are syntactically different from the original code. I mean, that's the essence of a mutant, but they are semantically the same. So they can't be detected. If you look on the right, I've got a very simple example of an original statement and a mutated statement. The original statement says, if X is greater than 10, we'll then assign X the value of 10. In other words, that statement caps X value at 10. It can be 10 or lower, but not higher when it leaves that statement. So in the mutated statement, you can see the little red highlight there. The relational operator's been mutated to include equality. So rather than greater than exclusive, it's now greater than inclusive, which means 10 will evaluate true. And that would be the aberrant condition you're trying to detect with this mutant's fault. But when you look at the statement that executes when that expression evaluates true, is it just assigns X equal to 10. So although it's superfluous, it has no logical impact on the program's behavior, because changing it to 10 when it's already 10 doesn't matter. So that mutant then is undetectable, and we deem it equivalent in that regard. And this is a very simple example. Most are in the wild are much more complex. And research shows it takes on average about 15 minutes to analyze a mutant and determine that it's equivalent, because they can be very challenging. So along those lines, and back to the bullets, they take an inordinate amount of time on the tester's part and result in no unit tests. So it's wasted time. Although I'll say tangentially, there's research, in fact, people from Google are saying the analysis is not worthless because it helps you detect code smells and refactor your code and improve it. But in terms of the unit test set, you don't get any more unit tests out of it. The last bullet is the most significant, and that is that the presence of equivalent mutants make it difficult to achieve mutation adequacy. And on the surface, you might say, well, of course, I mean, you can't get to 100% if you can't kill it. But remember, the definition for the mutation score is the number of mutants killed divided by the number of killable mutants. So the more equivalent mutants that are in the mix, the harder it is to get to that point. Anyway, so moving forward to the paper, I think poses 3 formal research questions, but informally, we want to know, are equivalent mutants the only real problem? I mentioned that this is the 4th in a series of papers about random selection, and the first of the 4 discovered that random selection performs almost as well as just selecting those dominator mutants if equivalent mutants can be taken out of the mix. So I'm curious, is that the only real problem mutation testers face? Secondly, are mutation selection strategies effective in that regard? Can they help you get there faster? And that's, again, with mutation adequate test sets, because I've got these 15 java.lang classes that the original developer tests have been augmented to make them mutation adequate. And lastly, and kind of tangentially, does mutation adequacy matter? Does all that hundreds of hours of work making those unit test sets adequate matter? All right, so the experiments in the paper, I'm not going to cover them all just because of time. That's just too much to do. But the main one I want to look at is the brute force attempts to identify the high-performing sequences. And in part, they subsume the ones above, because if the random selection, the random generation ought to generate those sequences in some form or fashion anyway. But I conducted millions of trials under the premise that if a special sequence exists, that it might be randomly generated, and we could then detect it, analyze it, and figure out how to reproduce it. In general, mutation selection strategies, the goal is to reduce the effort it takes to get through all the mutants, because again, they're just massive numbers of them. We're not interested in maximizing the score, and in fact, in our case, we have maximal scores anyway. The mutation adequate test sets, we always kill all the killable mutants. So the goal is to reduce the effort it takes to get that done. So the brute force experiments, I ran 10 trials of well, 10 repeats of 100,000 trials each. Again, it's so resource intensive, I couldn't run it start to finish. I have to break it up into pieces. But you can see the results down in the chart, the graph at the bottom for the 10 groups from left to right. And there's a red dotted line, 2 red dotted lines across the graph. They are 2 standard deviations above and below the mean, which is depicted in green, by the way. But the raw observations are there as well, and as well as a box plot for people who like those. So any number of ways to assess these. But they all look fairly uniform, which is to be expected. But the goal is to look across the bottom and try to find the low scoring outliers, because that's really what we're trying to determine is there a way to reduce how much effort it takes to get this done. And if you look at group 4 and sort of a little bit up from that label, the observations ended up on the left side of each column, but you'll see the absolute lowest trial that I've encountered, which is 15.56, I think. And statistically, it's significant here. It's way outside of the bounds of the data. But in terms of practicality, it turns out not to be terribly significant, because the difference between that observation and the mean is less than 100 mutants out of almost 12,000 mutants. So it's less than 0.1% of all the mutants. And so, but moving forward, I realized trying to figure out what made it and a couple of the other lowest outliers work that well. And I realized that the sequence of killable mutants encountered was repeated many times in the millions of trials, but the distinction was the number of equivalent mutants they encountered. So if I stripped out the equivalent mutants, I saw that pattern repeated many times. So then I moving forward, I wanted to try to check, well, are the equivalent mutants actually the problem? So I ran regression testing, not on just the equivalents, but on many of the mutants. But there clearly was a strong correlation between the number of equivalent mutants encountered. You see that on the x-axis at the bottom, and on the y-axis, the percent of mutants evaluated, or in other words, how much work the tester had to do to get to their mutation score of 100. And if you look at the OLS equation up there at the top, the y-intercept is 5.61. If you look down in the lower right, the inset graph I put there, I ran the random selections with no equivalence, and you can see it's very, very accurate. It's only 0.1% off. And when you consider that the range of data is only 50 units and it's 1,200 away from zero, it's like aiming a laser pointer across a stadium, I think. I tried to come up with a internationally accessible example to try to make that make sense. And I thought, well, basketball, the guy in the middle there, if he takes his free throw, he's roughly, even taking out, feet, yards, meters, and centimeters, it's about the 3 times the height of the average player. Not player, the average person. The players are taller, but basically 3 times the height of the average player. If you look down at the bottom of the screen, and again, I apologize about the pointer, but you can see that the accuracy of our regression is like taking that same free throw from 5 full courts away. It's very, very accurate. So let me bounce back there for a second. So you can see again in the lower inset right, when you run the random selection, and this is a lot different doing without a pointer, I'm sorry, but if I look back here, you'll notice the difference between the 2 standard deviations above and below the mean is roughly 0.2%. Is that right? 6.2 to 6. 3. Sorry, and if you come back here, you'll see it's roughly the same as my point. That the behavior is very similar. But what puts their discrete or concrete value on the left axis is the number of equivalent mutants. Anyway, sorry. Here it is graphically. I analyzed again the data for 3 groups here. On the far left, Dominators only, and this is the only place I've depicted the Dominator behavior, but right next to it in the middle is random selection of only the killable mutants. In other words, the equivalent mutants are removed here. And on the far right is all the mutants with random selection of everything, including the equivalent mutants. So you can see in the pink zone or the pink area, that's the cost of the equivalent mutants presence in the data set. And if you look at the green line down towards the bottom, the cost of random selection above, Dominators represent the minimal effort it takes to get through them. That's remember, the fastest way through the mutants is to hit the Dominators one by one. Random selection only very marginally increases that. In fact, the lower fence and the upper fence on these 2 box plots is less than 0.1% apart. The random selection is very nearly performing equivalently to the Dominators. So the answer to that question in the large, but from the first paper, is there is no strategy that beats random selection other than being able to pick the Dominators. And on the right now, you'll see I reran these experiments with you can see in the upper right, this is with the mutation inadequate test sets and defining the relationships. And you can see the Dominators on the left, they are they look like they're performing much better than they actually do. The pink and green lines in this side are the same as the pink and green on the left. It's almost like that's an inset, but the scale is different because this graph needs to be taller. You can see in the upper right, the random selection it's way over what it ought to be. And the random selection is also taking much longer than it should as well. And that's in part because they don't have access to the better performing mutation adequate test set. But the point here is that you can't detect these performance anomalies unless you have truly mutation adequate test sets. And in the noise of the second graph, there's the 2 coexisting problems in mutation testing again are the redundant mutant problem and the equivalent mutant problem. And people look at them differently and separately and trying to solve them. But the reality is they're 2 sides of the same coin. The right-hand graph gives you the impression that you can improve over random selection. But if you look at the left side, you realize you cannot. So basically, the only problem here are the equivalent mutants. Anyway, so contributions are, I probably just talked through them actually. Equivalent mutants are clearly the problem for mutation testers. And apart from their presence, mutation adequacy is relatively easy to achieve. And apart from perfect knowledge or knowing what the Dominators are, mutant selection strategies have no impact on performance. And lastly, mutation adequacy is necessary to observe the above. Anyway, with that, I'll apologize one more time about the pointer, but I'll open it up for questions if anybody has any.
Maybe I have one. You mentioned AI a little bit. So do you think this AI may help here, or we still have no hope?
Oh, actually, so I know another, you guys may remember, I'm working on my PhD right now, but one of my fellow students worked on machine learning to try to detect Dominators. And I've actually, since I realized that equivalent mutants are the only problem, I've started doing machine learning to see if we can identify equivalent mutants with ML. And I've had some success. I'm approaching it a little differently than other people are because, in research, you have to be different and novel, right? But with the mutation adequacy, I'm seeing different behavior than others. Just like the error introduced in the performance numbers I show you, the latest paper out says that ML can cut the workload in half. And I'm getting the same results, but when I run it without the mutation adequate test sets, it way overemphasizes, it gives false I'm getting tongue-tied. The performance looks fantastic, like it's almost perfect, but I know it's not correct. So I'm thinking that other people's results may be overstated based on the error of the introduced by the lack of mutation adequate test sets. But I've also, you know, I can cut a tester's workload in half at this point with mutation adequate test sets, and I'm doing that with this same real world data. You know, I know what's equivalent and not equivalent. So yeah, I think there is hope for it. I don't know that it'll ever be 100% accurate. You know, you've got type 1 and type 2 errors in your confusion matrix and all that, and it's interesting to work on. So people are doing it, I'm doing it, and so on.
We have another question, Mohammed.
Yeah, so thank you, Randy, for this great presentation. So maybe one quick comment is, yeah, again, language models are here, and language models are good at finding equivalent code, like code the similar behavior, right? And that would maybe give a different direction to where we should start looking at equivalency, right? Is it maybe something that you may want to think about, especially it's like trendy and everyone is jumping into it, which means that you will soon see people doing that for in this aspect, and you want to, by aspect, I mean, they're looking at code similarly based on language models, right? So maybe this is something we should also, as people who care about quality, we should also look at the quality of that as well, right? And maybe another question that I have, because I do mutation testing as a user, you know, and I noticed that the equivalent mutants, they differ from one type of code to another. Different behaviors, they experience different types of equivalent mutants. And I haven't seen anything about your presentation talking about the software under test. So what I'm saying here is, do you think that whatever you have shown today is specific to one type of program, or it can be generalized across multiple programs?
Those are great questions, number one, and those are also relate to you know, threats to validity, obviously. You're right about language. The language structures are different. They lend themselves to different kinds of mutants. Even different mutation testing tools have different mutation operators. And I didn't talk about that because I tried to cut this hour-long talk down to 20 minutes today. So I left out a lot of those facets. But yeah, you're correct. And I've tried in my research to focus on things that I think are generalizable and will project to those other environments. And they, like in my case, there were the developer unit tests left on average 21% of the mutants unkilled. And people, and I'm working in defects4j, if you're familiar with that. So it's an environment people are doing research in, and they typically just deem the unkilled mutants equivalent and say, let's look at the results. But my effort to augment those unit test sets to make them mutation adequate, and I've got 18 subjects, 15 non-duplicate subjects, and 12,000 mutants. I've carved that down to only 10% that are equivalent. So literally cut that in half. So the results are going to be different based on that, and the training of classifiers is going to be much different when you have, you know, because there's no correlation between the deemed equivalent set and the truly equivalent set, other than they were hard to kill, which is why they don't get killed. So yeah, all valid points. And I'm defects4j and using the major mutation framework, Rene Just's tool, and it already tries to generate a reduced set of mutants. So other tools generate more mutants and different mutants, but I do think, I think the results are generalizable. People may not get my exact numbers, like maybe it doesn't go from 20% to 10% unkilled. Some places it's as high as 40% of mutants are unkilled. So, and it's not, you know, I've got the 15 subjects are not all identical. Some went from 50 to 10% mutants, and some I went from 30 to 25, you know, there's variations in the mix. So yeah, then that's why I try not to quote exact numbers too often, because they're always going to differ. But I think in terms, you know, in the large, like in the direction of goodness, I think these are generalizable results. And sorry, you asked the first question and I forgot what it was now.
Oh, no. That's answers your. My first question was more of a comment saying that language models should be part of your investigation because
Oh, yeah,
everyone
yeah.
is.
And
Yeah.
sorry, let me make a quick comment on that, though.
Yeah.
Some early research tried to use compiler tools to discover equivalent mutants, because it's all about the RIP model. You go to reach it, you have to infect it, it has to propagate, you have to observe it. And compilers are good at, like IntelliSense now, even in IDEs, they can tell you, oh, that statement's not going to be reached, And I think the same kind of programmatic analysis could detect equivalent mutants. It's just got to tackle it and do it, But I think it's feasible. I think it's feasible, at least in part. I think the compiler related research years ago was successful to an extent as well. Nothing, and I think it's an undecidable problem actually, is how many mutants are equivalent and which they are. But yeah, all interesting stuff. I've like I said, I've started moving in the machine learning direction myself, but to be honest, I kind of think that the compiler side has more promise. But I only have so much time to do things. So yeah, I'm in the machine learning first. Anyway, thanks. Good questions.
Yeah. I think, in my opinion, for ChatGPT, nothing is undecidable now. So, so they eventually will.
That's what ChatGPT tells you, right?
That's right. Yes, that's right.